China did something that sounds impossible. In Guizhou province, engineers faced a mountain separating two valleys and chose to cut straight through it. Instead of winding down to the river and climbing back up, they carved into both sides of the mountain and built a highway directly across the gorge. The result hangs 565 meters above the river, making it the highest bridge on Earth. Here's why this extreme decision made sense. Let me show you why Guizhou province is one of the most punishing landscapes on Earth to build anything. Imagine trying to create a highway system through a region where over 90% of the land is mountains and plateaus carved by millions of years of erosion. Guizhou sits in southwest China, and its terrain looks like someone crumpled a massive sheet of paper and then poured water over it for millennia. The result? Deep karst formations, vertical limestone cliffs, and canyons that drop so suddenly you could stand at the edge and not see the bottom through the mist. For centuries, this geography made Guizhou one of the poorest, most isolated regions in China. Villages sat on opposite sides of valleys, sometimes less than 5 kilometers apart as the crow flies, but requiring 4-hour journeys on narrow, winding roads to actually reach each other. Traditional infrastructure simply gave up here. Engineers had tried for decades, creating roads that would take 3 hours to traverse what should be a 15-minute distance, zigzagging back and forth down canyon walls, adding dozens of extra kilometers to every trip. Guizhou's isolation wasn't just inconvenient, it was economic suffocation. Factories couldn't receive raw materials on schedule, hospitals couldn't get supplied reliably, young people left because there were no opportunities. The entire region got locked in a cycle where its geography became its destiny. By the early 2000s, China's central government was watching Guizhou fall further behind the rest of the country's explosive growth. While coastal cities were becoming manufacturing powerhouses, Guizhou remained stuck in the past because the land itself was winning. Now let's talk about what this bridge actually does, because the numbers reveal something profound. The old mountain roads meant roughly 4 hours between Xuanwei in Yunnan province and Shuicheng in Guizhou. With the expressway and the Huajiang Bridge, the actual canyon crossing drops to about 2 minutes at highway speed. Think about what that means. A farmer can now get fresh produce to market before it spoils. A manufacturer can receive a critical part the same day it's needed. A sick patient can reach a hospital while treatment is still possible. But here's the deeper calculation China was making. Every hour saved in transportation is an hour that can be spent producing, building, or creating value. Multiply that across millions of trips over decades, and you're not just building a bridge, you're manufacturing time itself. When travel time drops this dramatically, the psychological distance between places collapses. Cities that felt separate start functioning as one economic unit. A company that would never consider building a factory in isolated Guizhou suddenly sees it as part of an integrated region. Chinese planners argued that the time and logistics savings were so large, the project's economic benefits would likely cover its enormous cost far faster than a typical highway megaproject. When regions get connected this efficiently, people start making different life decisions. They'll take jobs further from home because the commute is manageable. Young people stop leaving because opportunities suddenly exist locally. The entire trajectory of a region changes. So why did this specific bridge need to become one of the world's highest? The answer is not ego, it's geometry. The Beipan River sits 565 meters below the level where the highway needed to run. That's what the terrain demanded. The mountains on either side rise to heights where a roadway makes sense. There was no middle ground option. If they'd tried to descend partway into the canyon, the approach roads would have become impossibly steep and dangerous. The only viable path was to span the entire gap in one shot. That decision created a cascade of engineering requirements. At that height, you're dealing with wind forces that would tear apart most structures. You're spanning about 1.3 kilometers between towers, which means every component has to handle stresses that push material science to its limits. The bridge had to be a suspension design because nothing else could handle that span at that height, but not a symmetrical one. The canyon walls sit at different elevations, so the two towers stand around 1/4 kilometer tall, with different heights. This asymmetry creates unusual load distributions that had to be calculated and compensated for. The main cables stretch several kilometers long and are built from hundreds of high-tensile steel strands designed to handle enormous forces. These cables have to account for thermal expansion in summer heat, contraction in winter cold, dynamic loads from traffic, and constant wind, trying to turn the bridge into a giant sail. Then there's the anchoring problem. The rock composition here is cast limestone, honeycombed with cavities from water erosion. Engineers had to locate solid rock formations, drill anchor holes up to 80 meters deep, and create systems that distribute forces across large areas, rather than concentrating them at single points. Now let's talk about how you actually construct something like this when the worksite is hanging in mid-air. Traditional construction methods assume you can put equipment on solid ground. None of that works here. The two sides of the canyon are separated by over a kilometer of empty air. The solution sounds like science fiction. Engineers first had to shoot pilot lines across the canyon using industrial rockets carrying cables. Once those pilot lines were in place, they used them to pull progressively thicker cables across until they had working lines strong enough to support a cable crane system. This crane could travel back and forth across the gap, carrying pieces of the bridge deck and equipment, but everything had to be positioned with extreme precision while dangling hundreds of meters in the air, often in high winds. The margin for error was essentially zero. When connecting bridge deck segments, if one piece is off by even a few centimeters, it creates stress points that could lead to catastrophic failure. Construction equipment used Beidou-based positioning and surveying systems to keep everything aligned to within centimeters. Then crews refined that to millimeter-level accuracy when connecting deck segments. The entire construction site became a digital system where physical reality and sensor data merged. Weather created another category of problems. Wind speeds in the canyon could change rapidly. Construction crews had to work in narrow weather windows, sometimes having only a few hours each day when conditions were safe. The deck installation took 2 years of careful, methodical placement. Each section had to be lifted, positioned, connected, and verified before moving to the next one. The bridge was designed to handle forces that most structures never have to consider. The canyon creates what's called a Venturi effect. Air moving through the narrow gap between mountains accelerates, like water flowing faster when a river narrows. On certain days, wind speeds can exceed 40 meters per second. That's hurricane force. Engineers designed the deck with careful aerodynamics. The shape was tested in wind tunnels to ensure air flows around and through it, rather than pushing against it like a sail. The deck has openings that let wind pass through, reducing the force while maintaining structural strength. But wind doesn't just push steadily. It creates vortices that can set up resonance frequencies. If those frequencies match the bridge's natural vibration modes, you get amplification. This is what destroyed the Tacoma Narrows Bridge in 1940. The Huajiang Bridge uses damping systems to prevent this. Inside the structure are devices that absorb vibration energy, acting like shock absorbers that keep small movements from building into dangerous oscillations. Then there's seismic risk. This region sits near several fault lines. The bridge needs to flex and absorb seismic energy rather than resisting it rigidly. The connection points between the deck and the towers allow controlled movement during ground shaking. The Huajiang Bridge is under constant surveillance by hundreds of sensors embedded throughout the structure. An array of sensors, including fiber optic strain gauges and GPS monitoring stations, continuously tracks how the bridge is behaving. These systems can detect strain, temperature changes, and vibration at thousands of points simultaneously. This creates a living map of stress within the structure. Engineers can see in real time where loads are concentrating, whether traffic patterns are creating unexpected stress points, or if seasonal temperature changes are affecting the materials. GPS stations on the towers measure movement with millimeter accuracy. The bridge moves constantly, expanding in heat, contracting in cold, swaying in wind. All of this is normal, but the GPS data ensures the movements stay within designed parameters. This is a shift in how infrastructure works. Traditional bridges were inspected occasionally and maintained when problems became visible. Modern megastructures are monitored continuously. The bridge becomes a source of data about itself, but there's a final layer to why China built this bridge the way they did. The bridge has become a tourist magnet, with viewing platforms and extreme height experiences built around it. It features heavily in Guizhou's bridge tourism marketing, including bungee-style attractions and glass walk experiences in the region's other high bridges. This was not accidental. When it opened in 2016, it became the highest bridge in the world by deck height. It remains one of the highest bridges on Earth, now second to the newer Huajiang Grand Canyon Bridge, also in Guizhou. It's a demonstration of capability, a physical statement that Chinese engineering can match or exceed anything built anywhere else. It's also a signal to developing countries considering infrastructure partnerships. China's Belt and Road Initiative offers to build similar projects across Asia, Africa, and beyond. When officials from countries with challenging terrain see what China accomplished in Guizhou, it becomes a sales pitch. The bridge is also an economic anchor for the region. Tourism brings money, but more importantly, it brings attention. Investors who might never have considered Guizhou see news about the bridge and start wondering what other opportunities exist there. There's also a domestic message. For decades, China's western provinces watched coastal regions grow wealthy while they remained poor, held back by geography. Projects like this tell citizens in those regions that they haven't been forgotten. So here's what the Huajiang Bridge really represents. For most of human history, geography determined destiny. Mountains meant isolation. Canyons meant separation. Difficult terrain meant poverty. What China demonstrated in Guizhou is that with enough engineering capability, enough capital investment, and enough political will, geography can be made irrelevant. Distance can be compressed. Time can be manufactured. Barriers that stood for millions of years can be erased in a few years of focused construction. The question this raises is profound. When a country decides that physical reality is just another problem to engineer around, what does that mean for how the future gets built? Because whoever controls the ability to reshape geography at this scale isn't just building bridges, they're redesigning what's possible for civilization itself. If cutting a mountain in half sounds extreme, wait until you see the highway China is carving straight into the Himalayas, a project with consequences far beyond engineering. Watch next China's highway into Nepal, a move the US can't ignore.